So discovering the electron led to a whole bunch of more questions. So there must be some positive charge then, because atoms are neutral. They're not positive or negative. So if there's these negative charges in there, there's got to be positive charges. Is it just these two particles? Are there a whole bunch of other particles in there? How are these arranged? Is this a solid sphere? Is there some sort of structure on the inside? Tons and tons of questions. So one of the early models that was proposed is called the plum pudding model. In the United States, we don't have plum pudding, right? A plum pudding is a British dessert, and the closest thing we have, I think, would be like a blueberry muffin. So you've got the muffin, the cake-like part, and it's got blueberries, and they're just kind of randomly distributed. So that's the idea here. So we'll call it the blueberry muffin model, right? And in this model, there was this sphere of positive charge, so that would be like the muffin part, and the negative electrons were just kind of in it, sort of randomly, and those would be the blueberries. So that was the idea. You have to start somewhere. Now, before we go on and talk more about that, we have to understand a tiny bit about radioactivity. So, some atoms are unstable, and they will emit tiny energetical particles. Will just shoot out of them spontaneously. And that was discovered at the end of the 19th century. But knowing about radioactivity, this allows scientists to probe the structure of an atom. There are 3 different types of particles: alpha particles, beta particles, and then gamma rays, which technically are not particles. And the alpha particles are positively charged, and they're the largest of the radioactive particles. And for more on radioactivity, come back for Chem 1B, Chapter 21. Okay, so 1909, Rutherford, who was a student of Thomson's, was trying to confirm Thomson's blueberry muffin model, right? So in this experiment, he has a source of alpha particles, and he's shooting them at this very, very thin piece of gold foil. So the blueberry muffin model has mass and charge that's spread throughout the entire volume of the atom, and that model would predict that these particles would just go straight through. These are small, massive particles. They should go straight through. So this is an illustration of his experiment. So here we have our source of alpha particles, little tiny, tiny balls being thrown at this foil. We're expecting them to go through. How do we tell what they're doing? Well, there's a detector around the gold foil that gives a little signal when these particles hit it. So most of the particles did go straight through. Some of them were deflected a bit, but some of them were deflected through large angles. Essentially, they were bouncing back. That result was highly unexpected. Rutherford, this is a quote from Rutherford, it was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So a bullet, 15 inches, shooting it with an appropriately sized weapon at a piece of tissue paper, what do you expect is going to happen? Oh, it's going to blow straight through the tissue paper. Oh no, it bounces back and hits you. That's shocking, right? That can't happen. So this was just very hard to believe result. But you do it again and again, it always happens. So what do you do with the model? Well, we've got to come up with a new model because the blueberry muffin plum pudding obviously wasn't right. So this is what was predicted to happen, that these particles would go straight through. And as a result of this experiment, Rutherford concluded that matter is not as uniform as it appears, and that there must be a small really massive part in the center of the atom, and that most of the atom is empty space. So now we call this the nucleus, and we know that it contains protons and neutrons, and then the electrons are going around in this space, but it's mostly empty. So that's why most of those particles did go through. They didn't run into anything. But some of them ran into the nucleus, which is extremely massive, and so it bounced back. So it's a little bit like, say you got an airsoft gun and you're shooting airsoft pellets at a volleyball net. Why? I don't know, but you are, right? So most of those pellets are just going to go straight through, right? Because there's big holes and then there's little strings. But if a pellet hits the string, there's this little airsoft pellet, it's probably going to bounce, right? Because it hits something more massive than itself. And so that's what's happening here. The particles that hit the nucleus are bouncing back. So from these ideas, Rutherford came up with the nuclear theory of the atom. Most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Most of the volume of an atom is empty space, and in that empty space there are tiny negatively charged particles. He's not saying anything about what those are doing. That was wise. There are as many negatively charged electrons outside the nucleus as there are positively charged particles, which are called protons, inside the nucleus. So the atom is electrically neutral. So this model was highly successful, but it had some issues. So they were able to determine that hydrogen contained 1 proton and helium contained 2 protons, which you then would expect that helium would weigh twice as much as hydrogen. But the mass of helium was 4 times larger, which suggested that there was something missing from the nuclear theory. So later work by Rutherford and Chadwick demonstrated that previously unaccounted for thing was due to neutrons. So neutrons are neutral particles inside the nucleus, so there's protons and neutrons in there. And the reason that helium weighs 4 times more is because it has double the electrons, but also 4 neutrons, which, two neutrons, which, I just lost that one. Hydrogen doesn't have. It's almost time to quit. Okay, so these neutrons, they have no charge, they're neutral. Neutrons are neutral, right? The mass of the neutron is similar to a proton, so you can kind of think of them as like the same sort of thing. They weigh almost the same. One's positively charged, one has no charge. So hydrogen has 1 proton, no neutrons. The helium has 2 protons and 2 neutrons, and so it's got 4 of these particles and weighs 4 times as much. So the nucleus is extremely dense. Over 99.9% of the mass of an atom is in the nucleus, but it occupies very little space. So the book uses a cloud analogy. We have a lot of fog here in the Central Valley, and basically fog is a cloud that's just down among us, right? So this is the same thing as fog. So electrons are like water droplets in the fog. They're really tiny, right? Negligible mass, but they're spread out over a large volume, right? So fog is mostly empty space, right? You walk through the fog and you might get slightly damp after a while, but you're not getting drenched because of all the water you're hitting. You're not getting hurt because you're running into things in the fog, right? It's mostly empty space, but we can't see through it because there's so many of these little tiny particles that are messing with the light. So that's the cloud analogy. Matter appears to be uniform. I mean, you look at the benchtop, and you don't really see individual pieces in there, right? But matter is not very uniform. So we've got the nucleus inside the atom. If the nucleus was the size of a period, then the electrons would be 10 meters away. So, where's my meter stick? Here's my meter stick. Right? 10 meters away. That's probably like from me to the door, right? So here I am, a period in an atom. And the electrons are over there by the door, that far away, in a sphere around me. And what else is in there? Nothing. It's empty space. If you had a grain of sand that was just nuclei, get rid of the empty space, get rid of the electrons. That grain of sand would weigh 11 million pounds. Matter's mostly empty space. Here's another example. So scaffolding, like they put up around a building, right? Actually, this looks a lot more like playground equipment when I was a kid. They had playground equipment made out of metal bars, and to keep it from being muddy underneath, they put asphalt under it. And yes, we fell on our heads. That explains a lot, doesn't it? Anyway, so here's a person for scale. So this is just ginormous scaffolding, right? The scaffolding has these strong metal bars, but in between the bars is empty space, right? Well, air. So if you zoom out, like put that in the center of a football field and zoom out, those fancy drones and stuff they have, as you get further and further away, that scaffolding is going to start to look like a solid object, right? Because as you try to look through it, there's enough solid here that you can't see through it anymore when you get a distance away, right? But if you come in and zoom in, you realize, oh, well, yeah, this guy can just very easily walk through the bottom of this. He just needs to be a little careful not to walk into the poles. So if this was 100 stories tall, the size of a football field, that would be the size of the atom. The nucleus would be the size of a pea inside of that. So how does matter just not pass through each other? Well, when you tap your knuckle on the table, it's like one giant scaffolding, your fingers, bumping into another giant scaffolding, the table. Both of these are empty space, but they don't fall into each other. Does that make sense? I need visual aids for this, but I don't have them. So matter appears solid because the variations in density are way too small for our eyes to see. Any questions?